Okay, now we've established the linear models that we found in the prior week, and we've talked about outliers. Now we can talk about, did the models we actually find, are they actually valid? Is it actually linear? We assumed they were linear, or we thought they might not be linear. We just took a guess based on looking at the graphs. So first off, for significance, data is obviously going to be quantitative and random when it's taken, right? They're paired, obviously, independent. The scatter plot shows an approximate linear. There is no outliers, so you take those out, which we talked about in the previous section, part 1. Okay, and the stuff's normally distributed. Okay, the x and the y. Okay, so the hypothesis test we're going to use. We're talking about the population rho, which is, it looks like a p, but it's rho. It's the Greek letter. Okay, because we use r, which is the correlation coefficient for the sample, right? So this is unknown, right? Otherwise, it's known, right? Because we did that from the sample. So basically, you assume that it's 0, which means there's no relationship whatsoever. Otherwise, you assume that it's not 0, thus there is a relationship. So we're typically just going to stick with the not equal case, which means where there is a relationship, because the other two are just if you want to specifically do a stronger test to prove positive or negative correlation, right? So basically, if you fail to reject the null hypothesis, the correlation coefficient is not significant, right? However, if you do, the population coefficient is significant, different from 0. Thus, there is probably a linear relationship, basically. So we're going to use the t statistic. Okay, and remember what you do once you've assessed that the model is linear by doing the hypothesis test, right? You have to think about the linear regression predictions. What can I use this model for? So if r is significant, if the scatter plot shows a linear trend, then you can make predictions using that model, right? The y prime or the y hat equation, assuming that what you're doing is in the domain of observed values. You can't go outside of those values. So basically, you have to do interpolation versus extrapolation, right? So it's the process of making estimates of unknown values between the known data points. Right, so you can't go outside the known data points, right? You can't go well above or below the range of data that you have. So if you have like an age range of 20 to 40-year-old people, you can't make predictions for 100-year-old or 10-year-old people, right? That's the idea. Okay. All right, so we're going to do this for all three of these, basically. Okay. All right, so let's go back and steal the t here. And go to the spreadsheet. We'll start with the car revenue. Okay. Let's plop that over there. Bring this up here. Bring this up here. All right. So remember, you have the t statistic and you have the critical t, right? So t statistic. I'll just call it t stat, and then we'll bump this down. Insert. And the critical, or t critical. Often they just do t asterisk for t critical, you know what I'm saying? They often do that. Okay. And then we'll do insert the p value. Okay. So, whoops, I just screwed that one up. Let's get another version of it. Okay, so the t stat is my r value times the square root. I have a numerator n minus 2, so it's going to be parentheses n minus 2, close paren, divided by parentheses 1 minus r squared, close paren. There's my t stat and my t critical. All right, so we have to think about what we're going to do here. So determine if there's enough evidence. So set up the hypothesis test. So again, it's either 0 or not 0. So basically, it's this or it's this, right? We're going to do the not equal one for our hypothesis test. Okay. We did the t critical, right? We want to draw and label the normal curve, basically. So this is our normal curve here. So as you see, what we found is We already found this here. That's our t stat, right? So we need these values here, t star, which is our t critical values. The question is, how do I get those? Well, this is 5% here, right? And this is a two-tailed test for the hypothesis. So that means this is 0.95, right? Which means this area here is 0.025, right? And this area here is 0.025. Okay. Let's erase this over here, actually make this a bit better. Okay, so this area here, 0.025. Okay, so from here to here, right? From here to here is 97.5, right? So t dot inverse 0.975 comma degrees of freedom 6 minus 2. So 2.77, what do we get in the picture here? 2.776, that's what we got. Okay, so this is my t value here. So if I do the area for the t, that's all of the area from here to here, which is not what I want. I want the area going this way. So I have to do 1 minus the t distribution, right? Because if I do the t distribution, that's going to be all this area, which I don't want. So I do 1 minus to get the area this way, which is what I'm looking for, correct? Okay, so 1 minus t dot distribution. Hope I didn't do equals. 1 minus t dot distribution, right? And then I'm going to click on the t stat, comma, degrees of freedom, this minus 2. Oh, what did I do? Oh, I didn't put the true for the cumulative area. So that's 0.00002. But that's actually, let's label this as the area. And then we'll move this down again, insert, and we'll put p value. Okay, so if I double this 2 times that, okay, I'm going to get the p value. Okay, so think about the reason why that is. So 0.3 zeros and a 2, 4, right? So this area right here is this 3 zeros and the 2, 4, right? Oh, just keeps going, sorry. Dot, 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 right? But this is 2 tail, so I have to double it, basically. You know what I'm saying? I have to double it, right? Because it's double the area for 2 tail. Okay, so what I'm finding here, what is the conclusion? Well, this is my p-value, what's my alpha? So if I go back to here, I'm using alpha is 5%. So alpha equals 0.05. So what is the conclusion? Well, this is clearly less than alpha, right? So therefore I should, let's send this out, right? What should I do? Insert. We'll box that up. Okay, well, we'll put the little box. We should reject the null hypothesis. Correct? So we assume there's no relationship, right? So rejecting the null hypothesis because this is clearly less, right? Also, it's in the shaded region, right? Which means the alternative hypothesis is what we believe, which is what? That the correlation coefficient is significant. So what does that mean? This is significant, which means this model that we found, right, wherever the model is, we can assume that it's good enough to be linear. Okay? All right, let's do this 2 more times. We'll copy all of this. We'll go to the absence grade one, and then we will, actually, we should probably move this down a bunch, huh? Insert. How many do I need here? I need 1, 2, 3, 4. Insert. Okay, copy those. Copy. Paste, and then we'll copy the formula in case you don't remember it. Okay. All right, so we're going to do the r value times the square root of the n minus 2 divided by 1 minus r squared, close paren, all right? So t critical, so we have to think about the picture here. So this one here, let's remember, so we have a negative 6 point something here. Whoops. All right, so we have a picture that's terrible, 0.99, because alpha is this, right? So we have clickety-click here, clickety-click here, this area, right, is 0.0, so half of that is 0.5, so we have the same thing on the other end, right? The area is negative, positive 0.05, right? So that's this. So the question is, this is my t star, right? And this is my t star, right? My t critical. So I'm going to shade that and shade this. So the question is, I just found a negative t. T stat, is the t here or is the t here, right? Because if it's here, it's not enough evidence, right? Because this is t0. Because it was like negative 3 point something, or is it here? Here's not enough evidence. I'm sorry, this is not enough evidence. This is enough evidence, basically, right? So that's the question. Okay, so if I go from here to here, that's 99.5, correct? Okay, so equals t dot inverse 99.5 comma 0, no, I'm sorry, degrees of freedom n minus 2, so I get this here, so it's plus or minus this basically. So if I go back and draw this, this is clearly left of this, because this is plus or minus that answer, right? Okay, so the area is t dot distribution, this value, comma, degrees of freedom minus 2, comma, true. And notice I didn't do 1 minus this time, but I am going to do 2 times that for the p-value, right? Because let's think about the picture here. Let's draw the picture again. Let's get the a and the b out of here. And we'll get the t over there, right? So we draw the picture. All right, we got 2 t's. This one is the negative 4. This one is the positive 4 for the t critical, right? 4.03. All right, those two right there. And then we have this one right here, which is the actual t, which is the negative 6 something, right? That goes there, which means it's in the shaded region, right? And this area is this right here, correct? That goes right here. Whereas this area right here is the 0.005, right? Because this is 0.99. Right? So if I double it for two-tail, I get the p-value that's right here, correct? So clearly this is less than this, right? As far as the area goes, right? So the t I found is clearly in that area, right? And the p-value is less than alpha, right? Because the alpha is the 0.01, right? So that's clearly less than that, right? Oh, I'm sorry. Wrong thing. Copy, paste, delete. Either way, it's still correct, right? Put that in the center and insert. So it's the same answer. We should reject the null hypothesis. Lock those together. Okay. Whoops, I didn't copy it though. Copy. Paste. So what does that mean since I reject the null hypothesis, right? Because we assume that there's no relationship, right? The correlation coefficient is not significant. If we reject the null hypothesis, we're assuming that there is enough evidence, right? There is enough evidence, so therefore this is significant, right? Which means we can use our equation to make predictions. It's good enough to be linear. Let's try the last one. Teacher ratio, which we thought might not work, correct? We thought no against this one. We didn't think it was very good. Okay, well, let's try this one. I'm going to take these, copy, and we'll put those there, and we will do the t equation. Put those there, put those there. Okay, so t-stat is the r times the square root of the n minus 2 degrees of freedom divided by 1 minus r squared. Okay. Alright, so if I do this one says 10% for alpha. Okay. Oh yeah, there are always two tail in these ones. Okay, so 10% for alpha. Okay, so if I draw this one, put this up here for now. Right? I'm going to get 90 here, and I'm going to get this area is 5% here, and this area is going to be 5% here, right? This is our t alpha divided by 2, right? This is alpha divided by 2, right? Right? Or t critical, or t alpha divided by 2, however you want to call it, correct? So from here to here is 95, isn't it? Right? To get that value. So the question is RT here, or is RT here? Which one is it? So if it's here, not enough evidence. If it's here, we have enough evidence, right? So I'm going to do t dot inverse 0.95 comma degrees of freedom minus 2, and the area, since that's a positive one, I'm going to do t dot distribution this comma degrees of freedom minus 2 comma true. That's the wrong area though. I need to do, oh, that's the wrong t also, 1 minus. I'm going to do this one here. There we go. Okay, and we got to do double that to get the p-value. Okay, so alpha was equal to 10%, I believe, right? That is clearly greater than that, right? Whoops, that is not a greater than. All right, so as a result, when I combine these all together, merge, we should copy, paste, and do not reject the null hypothesis, which means there's not evidence, right? So let's draw our picture here. Okay, so we draw our picture. 0.90, right? And we get our 5% here and our 5% here, 5% here, 5% there, 5% there. Okay, what did we get? 1.85, right? 1.85 negative, 1.85 positive, right? For the t critical, right? T alpha divided by 2, right? Or t star, whichever one you want to call it. It's either alpha divided by 2 or t star, both t critical, right? And then RT is 1.39, which would be right here, right? That's RT, right? 1.39 is clearly less than this, and we want the area going this way, which is why I did 1 minus when I calculated this, right? So that area is 0.10, which is clearly, this is more than that, right? I have to double it to get both sides, which is still clearly more than alpha, right? So there was not significant evidence to show that this is a linear model. So this is not significant, which means we've proved what we thought, which is this model is not good enough to be used for linear, basically. Okay? All right, now we've established the first two are fine, and the third one's not. We can answer the questions. Okay, so the first one says predictions for $150,000 in sales, and this one is $1 million in sales. Okay, all right. So let's go to the first one, and we'll take this, copy, paste, and we set it with 150. Okay, so we need A plus B times the 15, I believe, because I believe it's in tens of thousands, isn't it? Yeah, so it's billions of dollars in USD. Okay, so that one's fine. However, I can't do this one, millions. You're like, why is that? Well, if I look at my data, none of these are even close to millions of cars sold, right? It's hundreds of thousands, that's it, basically. So if I copy this and I do copy, paste, and do, what was it, 1 million, comma, right? That would be extrapolation. Okay, let's bring those together. Can't do it. Okay. All right, so you can do this one because it's interpolation. It's within the data values we have. It's somewhere in there, right? Because if you look at our data values, clearly it's in there, right? You know what I'm saying? It's in there. That's a reasonable offer. So that's 15. 15 is clearly in there, right? The million is way beyond. That's 150,000, whatever. Oh, no, that's yeah. So this is way beyond basically. So you shouldn't do that. That's extrapolation. Okay, so the next one, 10 absences and 20 absences. Well, if I look at the data, right, I can do 10 absences. Copy, paste, paste. I can put 10 absences here and 20 absences here, right? And I can delete this and put those together, and I can say, put those together, and here I can just say extrapolation, right? Because 20 is clearly beyond my data set, basically, right? Or the negatives would be if that was possible. You can't have negative absences, though, in this case. So 10 absences, right? So if I do that, that's going to be A plus B times 10. Okay, so I can do this because 10 is interpolation, which means it's in the data set. This value model is significant, right? And the scatter plot looks linear, right? So let's go back, right? Okay, the scatter plot looks linear. Yep. Okay. There was no outliers. We took those out, right? And we basically proved that it was linear, basically, so we could do it. All right, so the third one says, what is the prediction for the ratio of 12 teachers? Okay. Well, if I go to here, okay, move this down. We'll do here, right? And we'll put 12 teachers. And we're going to delete all this stuff. This is not a valid linear model. Okay? Because we didn't prove its significance, so you shouldn't be doing any predictions using this equation. We did not find significance on that, basically. Okay. All right, so that's good for that part.